Hey folks, we're going to go over 3.1 Basic Trigonometric Identities, and to begin I just want to show something that we already know. We know that we have the reciprocal functions, which we've been talking about. So if we discuss these reciprocal functions, we've got the cosecant of theta is equal to 1 over sine theta. And let's just kind of review why that is real quick. So remember, by definition, for any angle theta, sine of theta is equal to y over r. Okay, so if you start kind of on the right-hand side and you start with y, 1 over sine theta, and we can say, okay, substitution, I can say that that's equal to 1 over y over r. And then through algebra, basically, if you remember a little review on this, because we're going to be doing a lot of algebra today, proving trigonometric identities. If you have 1 on the top, you can put it over 1. So let's just put a little fraction there. This is a complex fraction times the reciprocal of the bottom, so that's r over y. So it basically just flips the bottom. So you have r over y, and we defined that to be cosecant theta. Okay, so you can review these and go through them, but it's kind of assumed to remember the relationship. Some of you have used the word inverse relationship, but it's not an inverse, it's a reciprocal. Inverses, we'll talk about those in the next few chapters, in a couple of chapters from now, but for now this is what we are dealing with. One of the most important identities that we're going to talk about is 3.1. So let me show you 3.1 and we'll talk about 3.2 in a second. This is very useful, the idea of tangent theta equaling sine theta over cosine theta. So if I wanted to show this, one thing to do, click that real quick, is we start with sine theta over cosine theta. And by definition, I know that sine theta is the ratio of y over r. And I know that cosine theta is the ratio of x over r. If I do a little math magic, I'm going to take the first fraction, y over r, and I'm going to multiply it by the reciprocal, r over x, of the bottom fraction. If you notice, r can never equal 0. That's assumed. So we have y over x. What is y over x? Y over x is equal to tangent of theta. I would encourage you to pause the video for a second and see if you can do the same thing for 3.2 identity, cosine theta over sine theta. Start that, and by definition, what is it equal to? And see if you get cotangent theta. So when dealing with trigonometric identities, it all boils down to this one. Cosine squared plus sine squared is equal to 1. This is a big deal, and from there I'm going to show you all of the other identities and how we can derive them from this special one. This is called also the Pythagorean identity, and you'll see why when we do the proof. Now, I want you guys to get comfortable with dealing in the xy plane here, and because this basically that will cover any theta. So this picture is in your book and the proof is also. So for any theta, we can draw some point on the terminal side, xy, and it represents, and they put absolute value because remember we're dealing with distance and it won't matter anyways. So do you see if we drop, and this is, I want you to be able to do this, you always drop down. This is going to be your reference angle. Drop it to the x-axis, okay, your perpendicular. So now the hypotenuse, and remember that's the distance from the origin. So if your picture doesn't have r stemming from the origin coming there to the point, then your picture is set up wrong. Some of you guys are doing that on the, I noticed on the exam, you're drawing like your triangle like this, and you're calling this r, and it kind of works, but you need to drop the perpendicular down to the x-axis from any point. So remember, this measures theta, and since it's in, if this were in the third quadrant, it'd be somewhere between 180 and 270 degrees, but that doesn't matter right now. I'm trying to get you guys used to the idea of this, so because I'm going to give you lots of previews for the unit circle when we jump into chapter 4. Okay, so here we go. We've got x, and you can do this absolute value of x squared, because then this will be true for all x and y. Y squared is equal to r squared from the Pythagorean theorem. All right. So because of this, we have x squared plus y squared is equal to r squared. Now, if you think about it, as long as r is not equal to 0, which we're assuming it wouldn't be the origin, because that wouldn't be a very exciting point, right? So we know that r is not equal to 0. So in that case, I can divide everything by r squared. And I can clean up this equation a little bit. I can say, okay, I have x, the ratio of x over r squared, plus the ratio of y over r squared equals, what's r squared over r squared? That's 1. What is x over r? X over r is, by definition, cosine of theta, and that is squared, plus y over r is sine theta, and that is squared, and that's equal to 1. Now, be really careful, because the way that we like to write our trig functions and square them is rather than on the outside out here, or like right next to here. Can you see that cosine theta square could be a little confusing? So that's not the proper way. So where we squeeze in the square, or the power, is right here. Cosine squared theta plus sine squared theta is equal to 1. Keep in mind, though, what this means is cosine squared theta is equivalent to cosine theta, quantity of that, cosine theta squared. Isn't that a lovely little proof and identity? So that's your best friend. Now we're going to prove all the other identities. 3.3. So I'm following the identity numbers, which are the same as in the textbook. So you can be thumbing through this as we go, and I would be sure to read it, like I said. Okay, 3.4, if you look, it has sine squared all by itself. So what do? You put that cosine squared over to the other side, and that's your next identity. Sine squared theta is equal to 1 minus cosine squared theta. Okay, let's do the next one. Let's do 3.5 on the same page. So if you have 3.5, write the Pythagorean identity. And the reason why I'm going to do this is I just want you guys to know that there is not much memorization here. If you can understand the Pythagorean identity, you are golden with everything else. So we have cosine squared equals 1 minus sine squared theta, and sine squared theta equals 1 minus cosine squared theta. Pretty easy so far, right? Okay, so what if I took the square root of both sides here? The square root of this side and the square root of this side. And I'm not going to write it out because I think you guys can see it. Square root of something squared is just that something. So sine theta equals plus or minus. We don't know what the square root of 1 minus cosine squared theta. And please do not say that that is equal. That is not equal to 1 minus cosine theta. Okay, that's one of those big algebra no-nos. And let me do a quick algebra thing example. If you had something like 1 minus x squared, that is not equal to 1 minus x, okay? Because it's like an order of operations. You have to do this thing first, okay? And we can't combine that. So it's just stuck like this. So sine theta is equal to plus or minus square root of 1 minus cosine squared theta, and that is 3.6. So you can see where 3.7 would come in. By taking the square root of both sides, we have cosine theta is equal to plus or minus the square root of 1 minus sine, don't forget your squared theta. All right, we're deriving a lot of identities here just from the Pythagorean identity. To prove identity 310, if we divide everything in this equation, the Pythagorean identity, by cosine squared theta Now think about why I can do that, because the only thing that cosine cannot equal in this case, just be sure, is it cannot equal 0, okay? Otherwise it wouldn't work. So just keep that in mind. Now cosine squared theta over cosine squared theta is 1. Now you have sine squared theta over cosine squared theta equals 1 over cosine squared theta. I'm going to do one more step, even though this is a little beyond. But sine theta over cosine theta, since they're both squared, I can write it like this. And this is the same as writing cosine theta like that squared. Now, by definition, earlier we saw that sine theta over cosine theta, this is a big one, is equal to tangent theta, and that's squared. And 1 over cosine theta, that's a reciprocal function, that's equal to secant theta squared. So if we clean this up, 1 plus tan squared theta equals secant squared theta. Okay, similar case for 311, proving 311. If you divide, assuming that sine theta cannot equal 0, I'm going to divide by sine squared theta. And you can do this in an equation as long as you do it to every term on both sides. So now cosine squared over sine squared theta, do you see that this is equal to 1 plus cosine theta over sine theta squared equals 1 over sine theta, and I can square this, that's equivalent. So cosine over sine theta is equal to cotangent, oops, and I wrote cosine theta. I'm going to just put the square there, plus 1 is equal to, and this, once again, is the reciprocal function right here, so that would be cosecant, and some of you guys are still getting those mixed up, and it's squared, cosecant theta. Okay, so like I said, I can derive all of these formulas just from the Pythagorean identity, and I want you to be able to do that, hint, hint, in the future exams and such. This is an important, it's not an identity because it's an inequality, but something to keep in mind that sine theta and cosine theta are always between -1 and 1. So they can range anywhere between -1 and 1. And if you think about it, remember, like if you think about some angle theta, so if we like draw this, and here's theta, and here's a point, and let's just pick a point in the second quadrant, let's say -1, 2. So if I find the radius of this, this is equal to, and if you draw the triangle, let me do a different color. If I drop down a perpendicular, so once again I'm dropping a perpendicular, I know that this length is 1, this length is 2, and this one would be, by the Pythagorean theorem, 1 squared plus 2 squared. Oops, I did my math wrong. It's the square root of 5. I almost said the square root of 3. So this, remember, x is equal to -1, y is equal to 2, and r, which is the radius, is equal to the square root of 3. So the idea for me, the way I think about this, is that the sine of theta is equal to the ratio of -1 over the square root of 3. Well, the deal is that the hypotenuse, which is equal to r, is always the largest, right? So in this case, it's the largest side. That's by definition in a right triangle. And so if you know that the hypotenuse is the largest side, right here, you're always either going to have a number that is, it could be equal to one another if you had like an equilateral triangle in there, but in this case it's going to be less than, this would make this less than 1, But since it's a negative thing, it's going to be greater than negative 1. So negative 1 over the square root of 3 is less than or equal to 1, and it's greater than or equal to negative 1. So I don't know if that example actually helps, but I just want you guys to start thinking about these reference triangles here by dropping perpendiculars and coming up with any angle theta. I think the book does a great example, and it has multiple examples of proving identities. So I thought that I would do some of the even problems from the exercise set, so then you can go back and look through the book's examples of proving identities plus my examples and go beyond. I would do the ones that I've assigned, plus I would practice some of the even ones later, test yourself, practice in a group. This is the hardest part of this lesson is the algebra. So being able to manipulate the equation and just going back to basic algebra and what you have to do, what you can do to an equation. So the first one is actually, they just want us to give an example of theta such that cosine of theta is equal to a negative output. So think about, when is cosine negative? So what quadrants would cosine be negative? Think about that, because we're dealing with theta, right? So remember that cosine theta is equal to x over r. R is always greater than 0, right? So r can be greater than 0, but x, when is x less than 0? When is x negative? X is negative in quadrant 2 and quadrant 3. So if you come up with anything in here, so let's just choose something. Let's do, what if theta, just for fun, is 135 degrees, which would land us right here. And the reason why I chose that, it's a nice angle. So this would give me 45 degrees here. And then if I drop a perpendicular down, and the point I'm going to choose, remember, as long as it's any point on this line right here, you can choose whatever you want. So I'm going to go over -1 unit, and then I'm going to go, since this is a 45-degree angle as well, by subtraction of 90 degrees, remember, then this side is also, so it's the absolute value of that, and this length is also 1. And this side, the hypotenuse, would be the square root of 2, right? So we could say that the cosine of 135 is equal to x over r. X is -1, r is the square root of 2. So this would be an example when cosine would be, theta would be negative. So you could say something like when theta is equal to 135 degrees. I'm not going to lie, number 3 is a bit of a doozy, but I'm going to help you guys through it. I want to give you some hints. One thing, what I would do is I would square the first equation, okay? And when you square, a little algebra review, the left-hand side would be a squared. You have to square everything in the parentheses. Cosine squared phi equals. Now, when you expand that, you're doing b v1 minus b v2 cosine theta, right? But then you have another one, b v1 minus b v2 cosine theta, right? So then you have to FOIL. So I'm going to FOIL the right-hand side. So b v1 times b v1 would equal b squared v1 squared. And then I'm going to do this, which would be, do you see how b times b is b squared? I have a v1 and a v2, and I have a cosine theta, right? Now I'm going to do this and this, okay? So I have another minus because of this negative sign. I have b squared. I have v2 and v1, so I'm going to put v1 first. And then I have cosine theta. And then the last term, this times this. So it would be plus b squared v2, whoops, I did it on the wrong. That's b squared up here, not a subscript. v2 squared cosine squared theta. So you guys can write this down in your homework. Okay, so how many of these, if I combine like terms, believe it or not, these are like terms, right? So I have, if I expand the right-hand side, b2v1 squared minus 2b squared, or not 2b, v1, v2 cosine theta, and then plus b squared v2 squared cosine squared theta. Now look at equation 2. So here's equation 1 and look at equation 2. If I square both sides of equation 2, you have a squared sine squared phi equals b squared v2 squared sine squared phi. Are you guys confused yet? Sorry. Way to jump into it, right? So I'm going to change colors. Now, if you see, this is where we're going to start using the Pythagorean identity because it's really important. This cosine squared theta is actually equal to 1 minus sine squared theta. Remember, if you get confused, just write over on the side sine squared theta plus cosine squared theta. It all boils down to this, equals 1. So if I subtract 1 sine squared over to the other side, I know that that's equivalent to cosine squared theta. So this is on the outside, b squared v2 squared, and I'm going to distribute this stuff to each of these. By expanding this, and remember on the left-hand side we have a squared cosine squared phi equals b squared v1 squared minus 2b squared v1 v2 cosine theta plus b squared v2 squared minus, let's see, we've got b2 or b squared v2 squared sine squared theta. This, look at this, what's that equal to? And that's, I just got that from distribution. This is from formula 2 here. Do you see that we can do a little substitution? So this is equal to, right here, if I bring this down, this is equivalent to a squared sine squared phi, and you've got all of this stuff. And we're trying to get, so if you bring this over to the other side and factor out the a squared, so I'm going to let you guys try that. You'll get the left-hand side, okay, because you'll find something like sine squared plus cosine squared theta, and that equals 1. On the right-hand side, you just have to do a little fun algebra, math magic, factoring out things to make it look like the right-hand side, okay, and then you're golden. Okay, so I know I'm a math geek, but I just really love proving identities, and I think it's just because it's like a fun puzzle. So if we try proving this identity, the trick is it wouldn't be very exciting and you wouldn't be able to do much if you started with this side. You start with one side. Here's our strategy. Start with one side and try to get to the other. Using given identities, the ones that we've already discussed. Identities. Okay, and that's in 3.1. So you can use any of those identities. Remember, I might ask you later to derive them from the Pythagorean theorem, some of those. I will expect you guys to know those identities. So with this first one, I'm going to start with the hard side and put maybe in your notes the hard side. Because if you started with sine theta, how would you even go about getting to cosine theta tangent theta? So we're going to start with cosine theta tangent theta. So we're going to start by saying, okay, let cosine theta tangent theta just be something. Here it is. Here's our expression. Now, and I want you guys to give explanations when you're doing this as well. What is the definition? Well, cosine theta is just cosine theta. We can just leave it like that. But tangent theta, we know that tangent theta from 3.1 is sine theta over cosine theta. Okay? And when you do this, I want you to say 3.1 or something like that. Or you could say sine theta over cosine theta equals tangent by definition theta. Okay? So I just want to know that you are using or what you're using so that it makes sense. So you have to give me some logic. It's kind of like a proof. So then we're going to cancel out just by algebra. You can see that the cosine theta and the cosine theta cancel out and you're left with sine theta. That is what we're trying to get, right? So then you get to put QED, which in Latin that's quod erat demonstrata. So you demonstrated that. It was to be demonstrated. And it's English, weird, funky English translation. To be demonstrated. So you showed that. Yay. Let's move on to number 6. So I'm going to start with the left-hand side. So I'm going to write the original thing, the left-hand side first, and I want you guys to do that. And then by definition, I'm going to say that tangent of theta is equal to sine theta over cosine theta. When you're doing these proofs, do not forget your angle, because it looks basically, if you don't have that angle like theta, it's tangent. Tangent must live with an angle. Okay, so you have to have any kind of trig function has to have an angle. If you just write sine over cosine, it has no significance. And you saw from that previous example in number 3 that we had two different angles. We had phi and theta. So, and then cotangent theta by definition. And so we could say that this is from, and you can do this in your exercise set, that this is from 3.1 once again. And then this cotangent theta is equal to cosine theta over sine theta. And that one, if we look in our notes, is from, what is that one? 3.2. So then my next step, I'm just going to do some math magic. I'm going to take the first one, the top, multiply it by the reciprocal of the bottom. You can say your explanation for this is math magic or algebra. And then that's equal to sine theta squared, because I have 2, I multiply straight across, and cosine theta squared. Sine squared theta over cosine squared theta. Actually, we don't even need to go to that. Cross that out, because right here, I should take it to be real technical. I should say that that's sine theta over cosine theta squared. And by definition of sine theta over cosine theta, that's equivalent to tangent theta squared, which is equal to tangent squared theta. I demonstrated that. QED. Now, I've noticed that students have a hard time with these identities, okay, from the past. The point is, don't give up. It's so easy to just give up and throw in the towel. But if you get frustrated at first, try again. It's not always easy, and it's not the easiest thing to see. But just keep playing around with the ratios and what they're equivalent to. Okay, we're going to try number 8, cosine squared theta, and I'm going to start on the left side. Now, I always want you to write down the original identity, because then it's a good reminder of when you get caught up in the thick of things, what is it that you're trying to prove? You're trying to start with one side and go to the other. So I'm going to start with the left, and this one, sometimes these aren't obvious. Sometimes you have to be a math teacher to know this kind of stuff, but I'll try to show you as many tricks as possible, and feel free to email me if you need a nudge to get started on any of these. So I'm going to multiply, it's like by the conjugate of this, and the reason why I do that is because I know it's the difference of squares down here. It's like if you have something plus another something times something minus that same something, I know that it's equivalent to the first something squared, which is just 1, minus sine squared theta. And then on the top, I'm not even going to multiply that. I'm just going to leave it as cosine squared theta and 1 minus sine theta. Now, I'm going to give you a hint. What does the bottom one look like? You guys remember? What's my favorite identity? Dun dun dun. Sine squared theta plus cosine squared theta is equal to 1. How can I get 1 minus sine squared theta from that? I just bring it over to the other side, right? So I know that this thing on the bottom is equal to cosine squared theta. The thing on the top I still have is cosine squared theta times 1 minus sine theta. Cancel those out. I'm demonstrated that the left-hand side is equal to the right-hand side, 1 minus sine theta, and then you always have to put your QED because you're proud of what you did. Okay, my hint for number 9, because it's not exactly like that, is you want to start with the right-hand side, and I would convert that first by definition sine theta over cosine theta minus cosine theta over sine theta. Then what you're going to have to do is you're going to have to get a common denominator. And the common denominator, it's just like adding fractions in algebra. The common denominator for this is cosine theta sine theta. So what is the left one missing? It's missing sine theta on the bottom. So if I do it, multiply it to the bottom, I have to multiply it to the top. What does that give me on the top? That gives me sine squared theta. The right-hand side needs a cosine theta, so if I multiply it on the bottom, I have to multiply it on the top. So that's equal to cosine squared theta. So I just combined this step. I went from here to here, and I'm going to see if you guys can see this connection. I'll give you a hint. In this case, see how I'm only dealing with in the top cosine squared theta? Well, can you get sine squared theta in terms of cosine squared? And that will be the trick to finishing that proof. For number 10 and 11, I'm just going to give you guys a hint. The idea is that you can factor that. It's the difference of squares, sine squared theta minus cosine squared theta, and you can check this by foiling it out, times sine squared theta plus cosine squared theta. Okay, what's this equal to? This equals 1 by the Pythagorean identity. Now you're just left with sine squared theta minus cosine squared theta. So number 13 is, I just wanted to get you guys set up. Definitely start with the left-hand side. And this one is a little complicated. So what you're going to do is you're going to write everything in terms of sine and cosine, and that's always a good rule of thumb. So you have sine theta, tangent theta is equal to sine theta over cosine theta, plus we have sine of phi. So notice we have two angles here, over cosine phi. And then on the bottom, cotangent is the opposite, so it's cosine of theta over sine of theta, plus now we have cosine of phi over sine of phi. Now what I would do is I would combine the top as 1, so get a common denominator, and in this case your common denominator is going to be cosine theta cosine phi, and it's going to be over whatever you get on the top. Think about what's missing here, cosine phi, multiply this by cosine phi and cosine phi. Okay, so you have cosine phi sine theta on the top, and then plus whatever this is missing. Same with the bottom, so it's going to be all over. Your common denominator in the denominator is sine theta sine phi, and you have to multiply this one by sine phi and this by sine phi because that's what it's missing, and this by sine theta over sine theta. So that's the hint, and you will see a pattern. The deal is, remember, you multiply the first thing when you have a complex fraction by the reciprocal of the second. So you're going to flip this bottom one and things cancel. Okay, I think that's enough to get you started. If you have any questions, I'll be in the AAC every Wednesday. Come and see me, send me an email, post some questions on the Q&A forum. Okay, have a great day.